Hey there, students. This is Mrs. Brunk again. Welcome back to Geometry A and to the wrap-up of Module 2, which has been all about transformations in the coordinate plane, slides, or what we call translations, rotations, and the translations, of course, were slid by vectors, right? Rotations in the coordinate plane, and reflections over different lines in the coordinate plane. And so today we're going to wrap up this module by looking at how that idea relates to symmetry. So I've read lots of different definitions of symmetry, and I thought I'd share a couple of them with you. The first one is symmetry in everyday language refers to a sense of harmonious and beautiful proportion and balance. In mathematics, symmetry has a more precise definition and is usually used to refer to an object that is invariant under some transformations, including translation, reflection, rotation, or scaling. So that's, definitely see how we're connected to what we've been studying. Because we've been studying the translations, the reflections, the rotations. And so we're going to see how does that tie in to the different kinds of symmetry. And then here's another one. The quality of being made up of exactly similar parts facing each other or around an axis. And that one's probably a little more of a functional definition because it helps us to be able to look at a figure and tell if it has one of the two different types of symmetry, either line symmetry or rotation symmetry. So we say that a figure has symmetry if a rigid motion exists that maps the figure onto itself. So remember we talked about rigid motion, and rigid motion is basically saying that it's some sort of transformation that does not change the size and shape of the figure. It just keeps it looking exactly the same, but maybe in a different position. So a figure would be said to have line symmetry, or what's called reflection symmetry, if a reflection maps the figure onto itself. Each of these lines of reflection is called a line of symmetry. So that's like the symmetry maybe we think of when we think about, say, the human body. Like, if you look on the outside, it's pretty symmetric. Most people, and a lot of times they say the more symmetric the human body is, the more beautiful it is, because it's just more pleasing and proportional for the eye. And so when you think about the symmetry line, it would just run directly down the middle, from the middle of your head all the way down to just kind of going through your torso, and then maybe smack dab right evenly spaced between your feet. So that would be like a line of symmetry. So reflection symmetry is one type of symmetry. And a figure has rotational symmetry if a rotation maps the figure onto itself. The angle of rotational symmetry, which is greater than 0 but less than or equal to 180 degrees, is the smallest angle of rotation that maps a figure onto itself. So let's look at these two kinds of symmetry. So up here in this first drawing, we've got looks like a crescent moon, and you can see the line of symmetry is drawn in right here. So the reason why I know that's a line of symmetry is the part that's up here on the top, this right here, looks exactly the same size and shape as this part down here does. And I can just imagine kind of folding the figure over that line, and it would map right onto itself, and I wouldn't even be able to tell that it had been reflected. So it would look identical. So that definition I read that basically said that it was invariant. Well, that's what they meant. So like it wouldn't vary at all under these transformations. Now the other kind of symmetry was that rotational symmetry. And so there's a center of rotational symmetry. It's like the pin that basically that's holding the figure down, and the figure is kind of turning around that. And at some point before it makes it 180 degrees, it maps onto itself so that it looks identical. So for instance, with this star, you could imagine that. In fact, that's 72 degrees, it would be going this way, like this. 72 degrees, I usually think of it going the other way, but if I had a point right here on the star, and by the time I rotated it 72 degrees, that point would be right here at the top, but I wouldn't be able to tell that it had been turned if I hadn't looked at that point because the figure looks identical. So that 72 degrees is the angle of rotation. That's how many degrees you have to turn it before it maps onto itself and you can't tell the difference. So an angle of rotational symmetry is a fractional part of 360. So that makes sense because 360 would be all the way around, right? And so notice that every time this 5-pointed star rotates 360 degrees divided by 5, or 72 degrees, the star coincides with itself. The angle of rotation for the star are 72, 144 degrees, 216 degrees, and 288 degrees. So basically every 72 degrees, if a copy of the figure rotates to exactly match the original, the figure has rotational symmetry. So with reflection symmetry, it's like there's a place in the figure where you could draw a line and fold the figure over itself. It would look identical. And with rotational, you could turn it a certain number of degrees and the figure would map onto itself and look identical. So those are the different kinds of symmetry. And now we're going to take a look at identifying symmetry in some figures. So our directions in the example say to describe the symmetry of each figure. Draw the lines of symmetry. Name the angles of rotation, or both if the figure has both. So if it has reflecting lines, we're going to draw them all in. Then we'll list how many there are. And if it has rotational symmetry, we're going to calculate how many degrees the figure would have to turn before it mapped onto itself. In other words, we'll calculate those angles of rotational symmetry. Okay, so first of all, looking at this figure in example A, the markings. Remember that these markings, when the tick marks are the same, that means that they're equal in length, and that's important to know so that we're not just assuming, hey, it looks like if I put a line here and I reflected that figure, that segment, say, would be the same length as the one on the other side, and it would map onto itself. So it just gives us some more evidence to show that that's true. And then the little arcs mean those angles are equal. This definitely has reflection symmetry. You can see, like, if you were to draw right here, see, that's a symmetry line, and I just need the other end. So there's one. Oops. There's another one right here. Right there. There's another one that goes right here through the sides. And another one that goes right here through the sides. And that actually looks like that's it. I mean, we could fold this figure along any of these lines, and we would have a figure that looks identical, and it would just map right onto itself. We would hardly be able to see it. So how many lines of symmetry is that? Well, there's 1, 2, 3, 4. And if I kept counting, now I'm recounting, because notice up here, that line has already been counted. And then when I get to this one's already been counted on the other side, where the 2 is. Get to this next one, this one's been counted on the other side where the 3 is. And finally, back up to the top, well, that one's already been counted as well. At the bottom, it's the 4th one. And so there's 4 lines of symmetry. So symmetry lines, or LOS, line of symmetry, there are 4 of them. Okay? So then maybe the angle of rotation, the AOR, angle of rotation. Now, what about rotational symmetry? So clearly this thing has rotational symmetry too. And when you think about, let's say you put a point right on the figure right there, and if you rotated it and brought it around here like this, it would map onto itself right here, and then back again here. It would land on itself, and since those angles and the sides are the same there, coincides right there, and then back around one more time, actually makes kind of a cool design when you draw all this stuff in there. And so you can actually tell that this thing maps onto itself 4 times. Starts here, 1 time there, then onto itself again here, then onto itself here, and then back to the beginning, onto itself. So the angle of rotation would actually be 360 degrees divided by 4, which is 90 degrees. That's the first one. Now they actually want us to list all the angles of rotation, so it's every 90 degrees, so 180, and then another 90 degrees when it gets to 270, and then back to 360. Those are the angles of rotation. Now one thing to notice, and this is not just a coincidence, that when this figure was rotating around and mapping onto itself, it was actually rotating around the point where those reflecting lines actually crossed. So that's actually the case anytime a figure has 2 or more reflection lines. You know, they'll always cross at the same point there, and that actually then creates the center of rotational symmetry. So if a figure has at least 2 symmetry lines, it will also have to have this rotational symmetry as well. Let's go ahead and take a look at the next one. This one's very similar, and you may kind of already be able to tell that because it has 1 less arm, it's got 1 less opportunity for symmetry there, right? There's 1, there's 1, and there's 1 right here. And that's all your lines of symmetry. So, and then these lines end up crossing right here in this point right there. And you can see that if I started with, say, a point right here and rotated, it would map onto itself there, and then here, and then back to the beginning, right? So we know that this has 4 symmetry lines. So lines of symmetry, I'm sorry, not 4, did I say 4? I mean 3. 3 lines of symmetry. And the angle of rotation then is going to be, this time it's 360 divided by 3. And 360 divided by 3 is 120 degrees. So the first one's at 120, then it maps onto itself at 240. And then when it gets back around to the beginning at 360, it maps onto itself again. So far, when we've seen that it has reflecting lines more than 1, we've seen that these values came out to be the same, that whatever the line of symmetry was, that's the number of times that figure would map onto itself as you rotate it 1 time around, and therefore the angle of rotational symmetry was 360 divided by whatever that number was. And it turns out that as long as you have 2 or more reflecting lines, that's actually going to be the case. They're predictive. They'll always be the same. So what about the square here? So the square has lots and lots of symmetry. It has the most symmetry of any of the quadrilaterals, because first of all you can go through the opposite angles. These are right angles, and those are symmetry lines. And then you also can go through opposite sides. And those are also symmetry lines. Oops. I didn't put that in the right spot. There we go. So this has also lines of symmetry. It's got 4. So it's got line of symmetry. It's 4. Your angle of rotation symmetry is going to be 360 divided by 4, which is again 90 degrees. So at 90, at 180, at 270, and then when it gets back around to 360 degrees. What about example D? So this time this looks like it's a trapezoid, but it's not an isosceles trapezoid. And in fact, if you think about this, kind of just envisioning where you could put a line, I don't see one at all. There isn't one. The only one that would even be close is maybe something like that, but you can clearly tell on either side they're not the same because this is a right angle and that's not. So no symmetry lines, no rotational symmetry. This just has none of either type. So what about this kind of arrowhead looking thing? So I can definitely see that it looks like there's a reflection symmetry line right here. So that looks good. But otherwise I can't imagine as I'm turning that line around there it would ever, you know, make reflection images again on either at any point around the figure. So it looks like there's just one line of symmetry. And if you kind of imagine turning the figure around, it's not going to map onto itself until it gets all the way around. So if that's the case, I mean, anything would map onto itself if you rotated at 360 degrees. So it has no rotational symmetry. So we see that there can be one line of symmetry and have no rotational symmetry, but what about the opposite of that? Could you have rotational symmetry but not have reflection symmetry? Well, if you look at this next figure and this kind of, you know, squiggle thing, there's clearly no reflection lines. I mean, you couldn't, like, say, people might think, oh, well, you could draw something like this, but then no, because when you reflect it over, the hook would be on the bottom and the hook that's on the top is on the left-hand side, but it's going down instead of facing up. And so there really is no reflecting line here. But there is a point right in here, like if you could locate it just right in there, that this thing would rotate around itself. So when this point right here would rotate around and when it ended up right here, it would look exactly the same, right? So it took 180 degrees to get there, but still it made it in one half turn around. So this actually does have rotational symmetry, and it has two, I guess we always called it twofold rotational symmetry, but so it has rotational symmetry, and the angles of rotational symmetry are 180 and 360 for this one. So now we can see that you can have one line of symmetry, you can have no lines of symmetry and rotational symmetry only. But the fact remains that if you do have more than one symmetry line, if you have two or more, then you will have that exact same amount of rotational symmetry. So that it is predictive after you have a second angle or a line of symmetry that when they reflect, or I'm sorry, when they intersect, excuse me, they create this center of rotation. So we're going to go ahead and make these next four you-try questions, and just want you to pause the video, look at them, and try to assess them for lines of symmetry. List all the lines of symmetry, draw them in that you see, and then indicate if it has rotational symmetry, what are the angles of rotation before they map onto themselves. So list them all out. So go ahead and pause the video now. Give G, H, I, and J a try, and then we'll tune back in and wrap up the lesson for today. Okay, so in these you-try questions, we had a lot of variety. We had figures that only had a reflecting line, just one, as in G, but no rotational symmetry. In I, we had one that had rotational symmetry and had angles of rotation 180 and 360, but that had no lines of symmetry. And then we had two that were very similar in terms of their lines of symmetry and the angle of rotation, and actually I didn't list them all out here. I should have listed them all here on H and J, but the other angles are every 72 degrees, so they would be, 72, 144, let's see, 144 and 72 makes 128. No, that's not 118, excuse me, 118. And then so on. So let's see, there's a few more, just a second. Oh, sorry, I mean 218. Excuse me, I mean 216. Jeez, I'm having trouble with this. 216. And then 72 more makes 288. And then finally 360 back to the beginning. So 5 lines of symmetry, and the angles every 72 degrees up to 360 degrees. So basically, most of the idea behind symmetry is very visual. I think we're used to seeing symmetry around us all the time, so it's usually something we can pretty easily identify. And really, the only true calculation here is how to figure out the angle of rotation, and that's just 360 degrees divided by how many times the figure maps onto itself, and that gives you your basically your multiplier for when your angles of rotation will occur. So other than that, this is a very visual lesson, just being able to look at things and be able to identify these two different types of symmetry. So that does it for this lesson and for this module. So thanks for coming to class.